going to take it all down to 0 just so you can see what this timer does. It gets all fancy in the last 10 seconds.
Might disconnect everybody.
Yeah, I did mute out. There's like a gong. Usually it does a gong sound at the end, but I think I turned that off for everyone. But the anticipation is building. Oh no, it didn't do the, it's supposed to turn like a different color. Oh, well.
Disappointment.
Yes, we'll work on that for next time. Oh, there it goes. All right. We'll start our technical seminar and our new program year here. A little delayed. You know, we had the Hurricane Ida come along and change plans for a lot of us, but hopefully everyone made it out of that storm safely and is getting life back to normal here, hopefully. So it is October, and we have our first technical seminar on PLC-based control system upgrades. And we'll turn it over to our guest speaker in just a minute. Just a reminder, we are recording this, and we will make this recording available afterwards on our YouTube channel, so you're free to watch this after the fact. Everyone's lines are muted, but we're using the Zoom meeting platform. In years past, we were using the webinar platform, which everyone was muted and couldn't unmute themselves. So in the meeting platform, you do have the ability to unmute and ask a question live if you'd like to do it. If you don't want to ask it live, you can always type in a question in the chat panel, and we will address that as we go. Perhaps maybe it's not until the end of the presentation, but we will answer your questions. So if you do unmute, we just ask, remember to mute back and keep the background noise as minimal as possible. All right, I have a couple of intro slides. First, introducing myself. My name is Wayne Welk, and I am the newly elected president of the ISA New Orleans section. So I appreciate everyone's vote. I know that I was the only one on the ballot, but I do appreciate the vote and the support as well. So look forward to serving here in the coming year or the coming term. And also a huge thank you to Dean Bickerton, who I know is on the line, for all of his years of in that role as president. Dean did a lot of work to keep the section going over the last several years, and I know he was looking forward to a little bit of a break from that role, but not too much of a break because he's actually taken on a bigger role at ISA. So he's not decreasing his workload at all. But Dean's still around and will help us out as we go. So again, welcome to our new program year. Looking forward to a great year coming up. Right now we have 2 events. We have the one, of course, today, and then we have an event, a technical seminar scheduled for November 2nd, which will be on overview of alarm management and ISA 18, the standard for that. That'll be presented by Donald Dunn. And Donald has done this presentation for, I think, at the division and maybe even society level. So he's a really good speaker. We're very lucky to have him present this topic for us. As we move into the new calendar year, 2022, we will, of course, fill the schedule with more seminars and events. Our board had a meeting yesterday, and we are kicking around some ideas, maybe like a tabletop and some other events as we go. And once the pandemic allows us to kind of get back together as a group, we would hope to do some bigger events as the year unfolds. And as always, we ask all of our members to always share feedback on topics and events of interest. We're here to, the ISA is here to serve our members as best we can, and we'd always love to hear feedback on what would you like to see, either topics and or events or various training. So speaking of the board, just want to kind of introduce our, this year's board members, this term's board members. And it's very nice because we have several new board members who have joined us. Christy Anderson is our treasurer, taking over for Roger Reedy. Roger's been doing that treasury role for a very, very long time as well. Ronnie Leday, who's going to be our guest speaker today, is on board now and our program chair. So he's going to be really helpful in getting some of our technical content lined out. We have Stephen Cothran and Ryan Curry are also on board as board members, so volunteering their time. And we've had many who have returned as well. So Jose, Mike, Leo, Eric Keller, Dean, of course, Ram and Roger are still on the board, and we always appreciate their input, and we appreciate all the people who volunteer their time to help make the ISA New Orleans section go. It is a volunteer role, and it is open to anyone. So in the section, so if you'd like to, if you're interested in volunteering to help out, we'd love to have you on board. Reach out to any of us, and we'll be happy to talk. Another thing that just to kind of show that we've updated our website. So I tried to make the website, when you land on it, talk a little more about us and our sponsors, and some of our things we do in the community and our volunteer opportunities, as well as recent news. So NewOrleansISA.org will always be home for kind of everything going on. But that being said, we also have ISA Connect, and ISA Connect is linked from here on the homepage. And so ISA Connect is kind of a tool that the ISA Society uses. It's on their servers, and it's a great platform for sharing conversations with members all around the country and world. So our NewOrleansISA.org is our kind of our external website. And then the ISA Connect is, again, you have to be a member of ISA to be able to get into Connect, but it has a lot of resources there too. So I invite you to look at that Connect site as well, if you haven't. And one last thing for me is just to kind of thank our section sponsors again, and just kind of bring awareness back, about our section sponsors. We have a deal going with our 75th anniversary, the Diamond Sponsorship, we called it. So you can support our section as a sponsor for $75. And if you are a sponsor, some of the benefits: you get your logo and your company info on the website. You'll get priority opportunities to present technical topics. You'll get some priority opportunities for our section meetings and sponsor our section meetings and events, as well as just helping us out, helping support your local ISA section and helping us fulfill our mission as well. So if you would like to have your company sponsor, please reach out to us as well. With that, I'm going to turn over to Ronnie and let him present from here on his topic. I just want to say that MS Benbow is one of our, if we had a tier system to our sponsors, MS Benbow would be one of our top tier sponsors, because not only do they are a sponsor, but they also volunteer their training room to us when we were able to meet in person, and they've always been a great friend to the ISA New Orleans section. So with that, I want to welcome Ronnie Ledet, and he will take it from here.
All right, thank you. Want to release control there? Perfect. Okay. Wayne, can you see that on there?
Yeah, so it's got the presentation mode though, or presenters mode on yours. You need to.
Okay.
It's like it worked beautifully in the test earlier.
Of course, yeah. Let me see.
Maybe swap displays or.
Yeah, stand by.
Still showing your.
Okay.
There you go. Perfect.
Got it? Okay, yep. Good. All right. Thanks, Wayne. Again, as Wayne mentioned, my name is Ronnie Ledet, MS Benbow. Currently the program manager at MSB, been here for 17 years. Received my master's degree from Purdue and hold a professional engineering registration, both in electrical engineering and control systems engineering. So I've got my contact information at the bottom of the screen, and I'll also put it up at the end. So if you guys have any questions or want some follow-up information, feel free to contact me. What I hope to do, if we have time at the end of the presentation, is discuss an industry-wide survey that we sponsored through Control Engineering Magazine. kind of the state of technical obsolescence in today's industry. But if we don't have time on that and you're interested in some fine reading by the fireplace this upcoming winter, you could just email me and I'll send you a copy of it. Just quickly, a little bit about MS Benbow. We've been in business for over 40 years, founded in 1978, privately held corporation. Right now, about 100 to 105 employees. I'll say we're a multidiscipline firm. We're really multidisciplined within the areas, several different areas of electrical engineering, specifically power engineering, instrumentation and controls, telecommunications, both on Wi-Fi as well as cellular and traditional wireless instrumentation. We also have some support engineering services, some on-site design and drafting capability at several local refineries, and also have some affiliate engineering agreements with other firms to provide turnkey services that would also encompass civil, structural engineering, mechanical, and process engineering as well. End-to-end project ownership. I mean, when you hear of MSB Consulting, we're really a consultant and a project execution company, ranging from FEED and feasibility studies all the way through detailed design and engineering packages, project management, technical oversight, startup and commissioning, as well as closeout services and ongoing technical support. So, having gone through that, thought we would briefly just talk about the origins of the PLC, since it's kind of an interesting story, especially for all of us nerds out there. Back in 1968, and again, in quotes, and you'll see why here, Dick Morley invented the PLC, the programmable logic controller, at least conceptually. It was New Year's Day, 1968. Like a lot of people, Morley has a hangover from the previous night's celebration, but also kind of odd. He had a proposal due for work that day. So being an ultimate procrastinator, decides to forego writing the proposal and starts laying the groundworks to develop the PLC. And some of the requirements that he set forth, which even today still make a lot of sense. No interrupts for processing, direct memory mapping, no software handling of, I'll call them overhead items or repetitive chores. So to kind of free up the programmer from having to deal with low level programming, kind of machine or chip based. Slow for whatever reason. He realized later on that was a mistake. Rugged design with no fans or forced cooling, and also somewhat of a straightforward programming language, which back then compared to today really wasn't that straightforward, but it was really what ladder logic progressed from. Typical boring fashion, the product originally was called 084 because the company he worked for at the time, Bedford and Associates, it was their 84th project. So after he laid out all of the groundwork and really saw kind of potential for this, he and several of his associates left Bedford and started a new company, which was known as Modicon, which was kind of a partial acronym for Modular Digital Controller. So in starting up his new company, and when the design team was put together, one of his rules, actually his only rule, was that it wasn't to be referred to as a computer. He didn't want any misconceptions of what this thing could do or couldn't do. So, and ultimately from that, the programmable controller or programmable logic controller name came forward. Interestingly enough, about the same time that Morley was working on the 084 at Modicon, a team at General Motors was also independently working on a similar design that was strikingly similar. And Dick Morley, being the humble individual that he was, really never did take credit as the inventor of the PLC. And one of his quotes, quite interestingly enough, was, it invented itself because there was a need for it and other people had that same need. So very humble in his approach and his methodology in laying down the groundwork for what ultimately would become the PLC. Kind of also interested that he actually chose to refer to himself as the father of the PLC, which, okay, kind of a little bit odd, but I guess there's a little bit of oddity in all engineers. So, okay, moving along now that we've dispensed with the intro. Reasons for a PLC upgrade. Now, why would you want to go in, start a new project to put in place a PLC-based control system? Well, there's really a lot of reasons. We're going to focus on one of those today, but it kind of ranges from the replacement of old, outdated, lower technology systems, going all the way back to relay-based controls, hardwired. Replacement of electromechanical and hydraulic and pneumatic-based control systems. But really what we're going to focus on today is the replacement of old, outdated, obsolete PLC control systems. So you saw when we first started out, the PLC was quote unquote born back in 1968. So that's been quite a long time. And through that time, all the way up to today, there's been several iterations of PLCs, even within certain brands. A lot of those are obsolete now. A lot of those have been replaced by more technically efficient systems. But I'm sure, we all have been on site. Let's say if you're getting ready to kick off a job, you're looking at some older control system and you walk into the control room and the operators will point to that panel all the way on the other side of the control room. It's like, look, this is the system we want to replace. We want to get a price to update that, but you can't open the door of this panel. You can't touch it and don't even look directly at it, right? It's so, a lot of these systems really just hanging on by a thread. And, the main issues facing all of these older systems today is really obsolescence, end of life, difficulty, or really refusal to support as these systems become obsolete from the manufacturers. Hard to identify, locate, and source spare parts. A lot of people have resorted to purchasing spare parts on the third-party market, eBay and other places, getting those parts in and then sending them to some type of certification company to go through and test and repair and update those. So that's a lot of time and effort to what ultimately would still be, a suspect piece of equipment or potentially unreliable. And the same goes for the software development toolkits as well. The system, the engineering toolkits that are used to develop the programs, download the programs into the PLC, as well as troubleshoot the systems. And a lot of these older toolkits, run on operating systems. I mean, it really hasn't been that long ago, I'll say within the last year or two, that I've gone out to take a look at a system and the systems were still operating on older DOS-based systems or a dedicated type of programming device, hardware device. And then kind of wrapping up this slide here, lack of technician knowledge on troubleshooting, maintaining, making changes to older systems, as a lot of these people who are familiar with these systems have retired, have gotten laid off, or have died, quite honestly. So a lot of, and this obsolescence, I mean, as technology advances, I mean, there's no one company that's immune from this. Rockwell, Allen Bradley, the old General Electric FANUC line, 9030, 9070s, Texas Instruments, which was a system that was ultimately bought out by Siemens, ICS Triplex, which was bought out by Rockwell on the triple modular and fault tolerant side, Modicon, keeping their legacy 84 there with their 984 and 800 IO series, as well as many others. So across the board, it's kind of like the nuclear arms race, right? As soon as somebody builds a better nuclear weapon and delivery system, somebody else is going to develop something to defeat it. So it's inevitable. Today's PLCs that are available, and this is just kind of a short list of what's out there in the market right now. Rockwell Control Logics, Compact Logics, Siemens Somatic Controllers, Modicons, Delta V, Triconics, Rockwell Triplex, Honeywell. Some of these are dedicated simplex only. Some of these are available in a fault tolerant, either hot backup standby mode all the way up to triple modular redundant. So a lot of flexibility within the product lines there. As far as applications go, again, somewhat of just a snapshot. There's many other applications as well, but sequencing and protection, batch control, process control, manufacturing, auto manufacturing, integrated circuits, rotating machinery control, gas and steam turbine control, compressor anti-surge control systems, as well as SIS systems, or safety instrumented systems. So, the PLC has really come a long way from just strictly being a relay replacement device to being able to run a host of flexible programming languages in addition to its own native programming languages. And, if you look here, you've got a full suite of the IEC 61131 programming languages: ladder logic, function block diagram, sequential function charts, instrumentation list, structured text, as well as other languages which certain PLCs or programmable systems can run. For instance, C programming language in addition to their own brand specific or native programming languages and environments. And everybody's familiar with the ladder logic. The beauty of this initially was that the people in the field, the technicians, were very familiar with troubleshooting, making changes in much the same way you'd wire up a relay. You'd put together your ladder logic. Then function block programming, which really has kind of come into its own over the past, let's say, 10 years or so, with the amount of flexibility, and as the library of function blocks continue to grow, and the ability to develop your own proprietary function blocks as well. Sequential function charts, which is kind of more of like a flow chart style of programming. Instruction list. Here's one you really don't see a lot of anymore, which is really, I'll liken this to more of kind of an assembly language or lower level programming environment. Structured text, which is somewhere between, a basic style programming language, but not quite as sophisticated as some of the higher level programming languages like C, which gives you, a lot of flexibility in terms of data structures, access to inputs and outputs. So, one of the nice things about the C programming languages, and when it first came out, it was one of the first higher level programming languages that really gave you access in a pre-developed way to the outside world via input and output structures and pointers. So, okay, we've talked about some of the reasons why we're going to upgrade. Now the question is, what are we going to do? How are we going to do it? What is the approach that we're going to use to upgrade our system? Specifically, what type of PLC are we going to go with? And also, what SIL rating do I need? What safety integrity level will meet my objectives with respect to availability, with respect to safety? So with respect to what type of PLC I need, some of the determining factors, and really some of the most important ones, is you want to look forward with one of your ultimate goals being standardization. So what is the prevalent PLC at your facility or at your site or company-wide? And what PLC is the enterprise transitioning to or will transition to? Because the last thing you want is to put in a lot of time and effort into a PLC system that will maybe not be obsolete because of its technical capabilities or because it's replaced, but because it's going to be a one-of, because the company or the facility has really moved to a different PLC. So now you have a system that's kind of a standalone. That's ultimately going to have to be replaced anyway. And also, another thing to keep in mind when upgrading to a newer PLC-based system is the migration path from the existing system. So do you stay within the same brand, quote unquote? What is the relative ease of migration? And we'll take a look at that. Some PLC brands are set up better than others with respect to migrating from their older legacy obsolete systems to their new systems, both in terms of programming environment, being able to take an older program and modify that to run within the new hardware platform, as well as replacing the IO. I mean, am I going to have to determinate all my existing wiring, my field wiring, and re-terminate? Are there certain solutions there that I could take advantage of? And another thing to look at, what are we going to go with in terms of redundancy? Does a simplex application meet our standards or our requirements, or we're going to have to go to some level of fault tolerance, whether it be a hot backup, a dual redundant system, a triple redundant system? Are we going to do that just on the CPU level? Are we going to do it on the IO module level? Or are we going to do it on the field device level? So a lot of questions there, and a lot of these questions lead to the question of SIL rating. So kind of talking about standardization, okay? And again, back to the first bullet item on our last slide with our ultimate goal of standardization. A lot of advantages on standardization, looking at, for example, spare parts commonality, okay? If we can reduce our spare parts inventory, we're going to go a long way to minimize with what I refer to as really a hidden cost. So if we can standardize on the PLC across the board, we can maintain a smaller inventory of spare parts for a larger number of PLCs. So for example, we'd only need to maintain a few analog input modules in inventory to back up many systems, as opposed to if we had several different PLCs requiring several different analog input modules. And before long, it can significantly add to your inventory cost and also complexity of having to maintain several different types of what's conceptually the same piece of hardware, but just for a different system. Take a snapshot here, and these are just kind of ballpark prices, but it's pretty illustrative of what you're dealing with here for a system. And you would have a CPU module, you would have a power supply, typically maybe an Ethernet module, some discrete ins, discrete outs, analog ins, and analog outs. So you have a system like this, maintain spares for that. you're talking about $25,000, maybe more, maybe a little bit less, to maintain a system. So if you can take advantage of and maximize this $21,000 spare parts inventory to serve several different PLCs, either through the facility or at the very least through a particular unit, you're going to go a long way to reduce your sunk cost in that system with respect to spare parts. And kind of along those same lines, same applies to the software development toolkits, which can also be quite expensive. If you have several different brands of PLCs at the facility, that means that you're going to have several different engineering development toolkits for developing logic, for making programming changes, for troubleshooting, and a lot of times even within a particular brand of PLC, you may require several different versions depending upon which versions of CPU or which hardware versions you have as well. And again, you're probably talking about somewhere between $2,000 to $2,500 for the cost of these licenses, less in some cases, more in others. Not to mention the cost involved in training your technicians to operate these toolkits, to make changes and to use them as troubleshooting devices, human machine interfaces, HMIs, whether it be some type of more of a generic HMI platform such as Wonderware, or a lot of PLCs have their own specific HMI development environment and hardware, which is more tightly integrated with the software that you're developing on the PLC, which cuts down the configuration and the programming time on the HMI end with respect to the development of the tag name dictionary and so forth. As well as communication interface. Now, there's been dramatic improvements over the last several years with respect to that. By far the gold standard on that is Modbus TCP/IP, but you still do run into some connectivity issues between the DCS, peer-to-peer sharing of information across PLCs. So if you have different PLCs, the level of difficulty with interfacing those goes up dramatically as well. So migration path, okay, how are you going to get from point A to point B? How are you going to go from your older system to your newer system? Well, some systems are easier than others to upgrade. Now, and this is just one I picked. There's others that have their own pluses and minuses as well. But Modicon, several different Modicon product lines have conversion routines for upgrading the current control software that's running on the older system to run on the new system. Now, would I run that conversion routine and just go ahead and put it in the new system and hit the start button? No, absolutely not. But it does make the task of updating the software significantly less labor intensive. And these can be applied to some of the older Modicons, to the newer M580s, as well as Modicon has some conversion routines that'll take the older AB PLC5s and modify and convert that software to run on the new Modicon M580s as well. On the field side, there's also some modifications, and again, others. This is just an example from Modicon, but other manufacturers offer this same type of technology to be able to take your old existing IO modules and upgrade that to the latest offering from the company, and to be able to do that without disconnecting the field wiring device is of significant value. I mean, we've worked on jobs in the Mont Bellevue, Baytown area, replacing 2,000, 3,000 IO points, and to be able to do that replace the hardware without having to disconnect the field wiring and re-terminating. Just cut, an immeasurable amount of time off the turnaround schedule. And essentially what it is, due to the design, the terminal on the older systems was a plug-in type. So we were able to disconnect that from the module itself and plug that into a terminating board behind the new IO. And the new IO was connected via ribbon cables to the old termination block. So really, an advantageous tool to use when updating the IO portion of these older PLC systems. So looking at safety integrity level, or SIL, question comes up, what SIL rating level do I need? And, the safety integrity level is defined as, a relative level of reducing the risk, which is provided by a particular safety function. A lot of times you specify that target beforehand in terms of your availability. But a lot of times what happens is if you ask the client what SIL level or rating do you require, they'll say, "Oh, give me the highest." Okay, well, to look at that, the SIL rating itself, it's a measure of performance required for each individual SIF. And by SIF, I don't mean software implemented fault tolerance. Really what I'm talking about here is the safety instrumented function itself. And what that is you could just think of that as the loop or the encompassing equipment that goes from detecting a certain situation to acting on that certain situation. So a safety loop is another way of thinking about the safety instrumented function. If you look here, for example, a high pressure shutdown, you would start at the pressure sensing device itself, goes into the PLC module, then the PLC processor and program. The solution is sent out via the PLC output module, and then ultimately to the shutdown device itself, whether that be a valve, a pump, a compressor, solenoid, relay. And note that the voting architecture itself is also included in the calculation and the safety instrumented function if it's designed into the system. So if you would have, for instance, dual or triplicated input modules, if you would have some type of fault tolerant output module, if you would have valves in series or valves in parallel, depending on what your requirements are, all that would be included in it. So how many safety integrity levels are there? Well, most of us have only heard of or are familiar with safety integrity level 3. There's actually a fourth one as well, SIL 4, but SIL 3 is the highest level that is economically feasible. And again, I'm sure we've all had conversations with clients when it came to fault tolerance and talking about, okay, what level of triplication do you require? What level of fault tolerance do you require? It's like, well, I want it all triplicated. It's okay, well, what do you want me to triplicate? The CPUs, the IO modules, the end devices? And when you give them a price for it, like, okay, well, what can we do to reduce this price? Maybe we don't have to be that safe. And looking at this here, the SIL levels, you've got really a couple of different ways of looking at it. You've got the probability of failure on demand, and that is essentially the probability that this particular safety instrumented function is going to fail when needed. And that can be either for low demand applications, like for instance, a discrete shutdown, which maybe, you wouldn't expect to happen often, quote unquote, versus some type of high demand or continuous mode application where that particular safety instrumented function is constantly being called upon to take corrective or protective action. So you could look at it as the probability of failure on demand, or also the risk reduction factor, where one is the reciprocal of the other. So again, example here, you got a risk reduction factor of 1,000. The SIF would fail during a dangerous scenario or when called upon to actuate once every 1,000 years. Now, what does that actually mean? Well, I could almost take two hands to count the number of 500 years floods we've had over the past 20 years or so. So, that really needs to be taken with a little bit of grain of salt. But again, that the other way to look at that, and the inverse of the RRF would be the probability of failure on demand, and that's essentially the probability that the safety instrumented function would fail when called upon to protect the system. And how do you go about this, determining the SIL level required? Well, there's a lot that goes into it, actually. The risk assessment, PHA, layer of protection analysis, and determining, based on what your availability targets are, the realistic test intervals, and whether those test intervals are implemented automatically through the control system itself, or some type of software implemented test interval, or manually, and whether that is online test intervals or offline test intervals. And a lot of that is really determined by what the test intervals are with respect to what's required to meet your availability targets. For instance, if based on your analysis, your testing intervals come out to be of a shorter interval than the turnaround time of the particular piece of equipment, then you need to do one of two things. You need to shut down that equipment more often to implement your testing to meet your required SIL level and your availability targets, or you need to design into the system the ability to conduct online tests, which really isn't trivial in nature. A lot of times what you have to do is not only modify the software itself to be able to handle online testing of these safety implemented functions, but you also have to physically modify the system. Whether you have to add another valve, for instance, let's say a shutdown valve in parallel to keep the system running while you conduct tests of the main shutdown valve, or a host of other things. So it could lead to some significant expense. And these SIL levels, kind of following up on what I was just saying, you can improve them by changing the system architecture, adding certain levels of redundancy, whether that be on the controller side, the input or the output side, power supply side, or the field instrumentation itself, or improving the probability of failure on demand by reducing the testing interval. And really what I mean by reducing the testing interval is increasing the frequency of testing. So let's say if the availability targets were such that you dictated testing this thing every 6 months, you can improve your probability of failure on demand by testing every 3 months, for example. A little bit of a caveat here. It's important to understand that just because you buy a SIL rated piece of equipment doesn't mean that that safety instrumented function, or worse yet, your entire system meets that particular SIL rating. And not picking on Rockwell here, actually I kind of applaud them in making this clear. They've got a 200-page manual just to explain how to use the control logic systems in a SIL 2 application, and kind of called upon here with, this equipment, while rated SIL 2, it's rated SIL 2 if you pay attention to and understand how to integrate this into your overall SIL rating strategy. So, important point to note. There's a variety of SIL calculation software toolkits available out there. We've got quite a bit of experience with SIL Solver by Systech. There's Excellentia by Exida, AE Shield, as well as a host of others as well. So a lot of those are really client specific based on what the client is familiar with or using in-house. So transitioning to a new system, some issues to address here. The new software development environment, surely the system to develop the new software, to maintain it, to troubleshoot it isn't going to be the same as what you're updating. The legacy software, the control software, I'll say typically, really almost always isn't easily implemented into the new hardware platform. Some are easier than others. Again, there's certain migration paths that you can take advantage of and migration toolkits. And another one, and I'm sure everybody who's worked on these types of systems on the upgrades will appreciate. I mean, existing software, I don't even know why I put usually, it's really always. It's almost always poorly documented. I don't know what it is about programmers, but they just want to get the program finished and they'll either not document it, or the documents and the descriptions of the programs and the comments are incorrect. They've gone back and changed the program, but they haven't updated the documents. Another consideration, which of the languages that we talked about do you plan on using? A lot goes into that. How technically savvy are your technicians? What do they feel familiar with? What do your engineers feel familiar with? What are the standards identified and developed by the client, either site-wide or company-wide? And also for the new system, what did your risk analysis, what did your LOPA, what did your hazard analysis identify with respect to the level of redundancy required and where? 2 out of 3 voting, where? At the controller level, at just the CPU level, at the IO level, at the field device and wiring level. So, kind of an interesting point here with respect to, we've talked about a little bit here, the added functionality, the flexibility, the advantages of going to a more technologically advanced system. But one of the things you need to take into account too, and I'll kind of liken this to the aviation industry. In the aviation industry, there's a whole science around identifying potential situations or problems when you make a correction to an existing problem. For instance, if you have identified a problem with a fuel vapor recovery system in the wing and you fix that problem, okay, well, by virtue of fixing that problem, did you create a latent issue that could lead to other problems? And the same thing goes with new PLC systems, both on the software side and the hardware side. And one of the most eye-opening examples of that is really the cybersecurity threat. A lot of these older systems didn't have Ethernet connectivity or sophisticated means to connect to a network. So, as the result of, having the quote unquote benefits of Ethernet connectivity now and being this tied into maybe your supply chain logistics system or taking advantage of the Internet of Things, you've also opened yourself up to cyber attack. And these can range from ransomware attacks to, catastrophic attacks. I was reading an article just this morning on the latest, rage with respect to viruses and it's not ransomware, it's what's called killware. It's specifically developed with the intent of causing not just capital and physical damage, but human loss of life as well. And I'll use with respect to the capital loss just a few months ago, Colonial Pipeline. Now, certain newer systems that are out, some of the newer systems come, I'll say, out of the box ISA secure certified. But again, the caveat there is how you apply that. The gap has seemed to close on the client's end a little bit with, okay, who's responsible for this? Is it the IT department? Is it the instrumentation and control systems department within the corporation? Or is it a combination of both? And really, it's part of an overall secure networking strategy, not just the PLC itself, firewalls and network switches all the way out to corporate interface. Briefly just talk about this. This is kind of interesting. I'm sure a lot of you have heard of this before. It was really kind of an eye-opening experience. Stuxnet, which kind of was the world's first digital weapon. And this attack took place at the Natanz nuclear facility in Iran. And what this nuclear facility was comprised of were a very large number of centrifuges. These centrifuges were large cylindrical tubes that were kind of arranged via pipes in what's called a cascade configuration. And this equipment would spin at supersonic speeds to separate the isotopes in a uranium gas. And the Iranians were using this for the production of weapons grade fissionable material. So, the attackers set forth a means and set in play a means to take out this facility. There were some challenges involved because all of the computers that controlled these facilities and these centrifuges were air gapped and completely isolated from the internet and from other networks. So, what the attackers did was they designed a delivery system to infect the controllers on site via a USB drive or several USB drives. And the way they did this was they identified target machines of companies and computers of companies that service this facility and infected those, and then that would proliferate throughout the internal network of the controllers on these centrifuges. And again, it was somewhat of an eye-opening experience because it was long thought that PLC systems, in this case, was Siemens S7-400, were immune from viruses and from control takeover. But in this particular instance, the Stuxnet attack was actually in two phases. The first one, it manipulated control valves within the centrifuge to increase the pressure, and it would destroy them. And then once all those repairs were made, the second phase was unleashed, which actually altered both the PLC program and, interestingly enough, the Step 7 programming toolkit itself, to alter the speed control algorithms to, one, overspeed the centrifuges to destroy them, but two, to fool the system into thinking that it wasn't overspeeding the system. So for all practical purposes, if you were looking at an HMI or even at the address locations for the actual speed within the PLC, you would think it was running at the desired speed. So none of the overspeed shutdowns took place and literally destroyed the whole system. So, I could talk about that more, but if you're interested in in doing some reading on this particular instance, there's an excellent book, very interesting. The hero of the story is the computer nerd, so I kind of like it. And it's called Countdown to Zero Day. It's available on Amazon. So we've kind of talked about the of how to get to which PLC we're going to use. Now let's kind of talk about the design process itself. And if we're talking about legacy systems, it usually involves reverse engineering the functionality of the existing system, and that's developing the I/O list, developing a functional definition of how the control system works, and a narrative explaining that in excruciating detail. And that's typically in the form of a general algorithmic description of operating, of how the software operates, both on the continuous and the discrete side of the control system. And it's important to understand that this should be a non-programming language specific description, so everybody can understand how this works, the technicians, the operators, without having the knowledge of any high-level advanced programming language. And then kind of as a follow-on to that too, for a little bit more descriptive explanation of how the discrete side works, developing the cause and effect matrices, and ultimately coming up with a verification of design. So verification of design really encompasses, what is the system supposed to do? And I'll caution you here that really need to pay attention to the carryover of errors, both hidden or latent errors and things that were supposed to work that were maybe never tested, that didn't work, or things that the client thought was implemented but was not implemented or implemented correctly with respect to functionality. And just like anything else, I mean, once this design is done, you would go through and conduct a very thorough review and defense of the design, and I'll liken it to defending a thesis in graduate school. And it's not until then, until this design, this general algorithmic design has been fully vetted, defended, looked at, verified, does the programming begin. And that really the overall goal of the software design cycle should be to try to reduce as much as possible the actual task of the software programming to that of data entry task. And what I mean by that is really just based on the control system documentation that was developed. That should be the Bible for which the actual software that's going into the PLC should be developed from. And the design shouldn't be developed at the keyboard. The programmer shouldn't just sit down at the keyboard and say, okay, the system needs to do this. And kind of starting that out, kind of a straightforward example of that is the cause and effect matrix itself, which is, a collection of causes and a corresponding effect. Essentially, it's a graphical representation of if this, then that. And I think it's straightforward enough. I know we're kind of running short on time. I won't go over the cause and effect itself, but I will talk about quickly, how do you begin that? Okay, you define the system in terms of inputs and outputs. If you remember from school, similar to a transfer function. A transfer function is defined in terms of its outputs over inputs. And this process would be to first define the inputs, then define the outputs, and define the relationships between the inputs and the outputs based on the system requirements, safety requirements, operational requirements, and a detailed review of the operation of the existing software. And to look at that, we would imply what's called convergent design philosophy, where you would start with the inputs and the outputs and work toward the control system software. And what you don't want to do is you don't want to start writing the software and then figuring out how to map that to the inputs and the outputs. That's really more of a divergent design philosophy, and I'll liken that divergent design philosophy to something that we're all familiar with here is a spaghetti plot. I mean, you just don't know where all that stuff goes. If you start at the inputs and the outputs and you work in, you're going to be guaranteed of picking up all the operational requirements. So cause and effect matrix, again, I'll kind of wrap this up here. I think we're all familiar with what the cause and effect matrix looks like. Input descriptions and items on the left side, output descriptions and items on the upper right side. So in summary, technology continues to evolve as usual. I mean, think about it. How many people have the same computer they had on their desk, 5, 6, 7 years ago? Besides my parents, maybe. Many options to consider when upgrading an obsolete PLC. One of the key focused issues that you want to concentrate on is standardization. Many benefits involved with that. Validation of legacy software is key to a successful transition to make sure there's no either carryover of mistakes or omission of functionality that the client thought was there but never existed. And this presents an opportunity to transition to a more reliable and safer system via risk analysis and the implementation of a lot of functionality and technical advantageous items that really weren't available when the obsolete systems were first put in. So again, that wraps up things. Unfortunately, I didn't have time to go over that survey, but if anybody is interested in taking a look at that survey, you can email me and I'll reply to that with a copy of the survey itself. So any questions on that?
Open up the questions for chat in or ask live. We can hang on here. I guess, Ron, I don't know if you have a hard stop or not, but we can hang on for a few minutes if
I'm good. Yeah, I have a few minutes.
Yeah, I guess this is Charles. Can you talk a little bit about HMIs and the recent struggles for securing them through the supply chain? Because there seems to be a lot of disruptions these days.
In terms of the availability of being able to get HMI hardware in, or
Yes. Yeah. I mean, a
well,
lot of us have upgraded the HMIs from like status lights.
Yeah, I think a lot of that. I mean, it's kind of the perfect storm of events, and over the past, I'll say 2 or 3 years. I mean, a lot of it has to do with COVID itself, with supply chain issues for integrated circuits, and it's not just limited certainly to HMIs themselves. I mean, I don't know if you've noticed if you've driven past a car dealership lately, like, I've driven past Lamarck Ford. I mean, there's hardly anything on those lots right now. And, there's a lot of, theories out there right now and talk about, future wars won't be fought over oil. They'll be fought over the resources, both natural resources and technical resources, to be able to produce integrated circuits. And I think, you're starting to see that propagate as well into several facets of our lives. On the HMI side, I have a whole house generator for my house that went down during Katrina. I'm not Katrina, during Ida. That's going on 6-7 weeks ago, maybe a little bit longer, and I'm still waiting for the spare parts for that to come in to make the repair. So it's just, and unfortunately, I think we're going to see more and more of that. Is that the demand is such that it can't keep up with a hiccup in the supply chain logistics to get all this stuff built.
Appreciate it.
Mm-hmm.
Don't get rid of those pilot lights yet there, Charles.
Yeah, no kidding.
All right, we'll give it another minute or two for last call for questions here. I was say that was a very good presentation, Ronnie, and I love the engineering approach to it. I know a lot of times I think we're guilty of looking at a PLC system and saying, "Oh, that's straightforward, just replace it and convert the program and go." But the fact that there is a a very detailed engineering approach to it, even what seems to be a simple project,
Mhm.
is a very smart move. I would say yes. Okay, well, sounds like no additional questions. I know we always get I get a barrage of emails about PDHs after. I will send them out hopefully in the next day to anyone who, everyone who registered. There was a question about, do you need PDHs? If you answered yes, and you are attended or have attended, I will send you a PDH by email in the next day or two. If you need one and said no, just reach out to me and we'll be happy to get you a PDH. And with that, I want to thank everyone for attending. I want to thank Ronnie for the great presentation, and we'll look forward to seeing everybody in November, online, of course.
Sounds good. Thank you.
Okay, thanks.
Thank you.
Thank you.